Good evening, ladies and gentlemen. Welcome to Lecture 9 of Topic 1 of Unit 4 Electromagnetic Waves. This video will be covering the main ideas of Chapter 8.5 of Book 2. Please complete the reading before class. Here are your learning intentions and success criteria for the chapter. Please pause the video and attempt to complete the KS table down on the bottom right. Okay, we can see we've got a shorter one here. The big goal here is that we want you to be able to explain electromagnetic waves in terms of electric and magnetic fields. So that's your first criteria, that you need to be able to do these from both E and B fields. So remember, B is our symbol for magnetic fields. And I want you to be able to apply the wave equation to questions on light. We're not going to practice with that today, but it is something that we should be able to do, because any questions that ask you about light will also ask you, we basically be using this equation we've already learnt about. So in terms of our knowledge and skills, we need to know what is an electromagnetic wave. If we don't know what it is, a bit hard to explain it. How do these two fields, our B fields and our E fields, influence electromagnetic waves? And then what is the wave equation? And then finally, how do you use that wave equation on light? What sort of special things do you have to do? After you know that one special thing, it's just a typical wave like we saw in Unit 3, Topic 3, when we looked at waves. So, let's do a little bit of history here. In the 1860s, Faraday's work on induction that we looked in the last couple of videos was well known. Electricity was the big deal, but there weren't any real laws about it because Faraday's math skills weren't that great. Remember, he got his entrance as a bookbinder because he didn't do a formal education when he was young, but he was very inquisitive about these things. Maxwell came along. Now, Maxwell took Faraday's work and applied a lot of mathematical rigor to it, and he developed 4 equations that explain electromagnetic observations. Now, we don't need to know Maxwell's equations, but it's important to know sort of how this came about. And one of the things he tested, or he asked about while he was working on his 4 equations, were how fast do electromagnetic waves travel? Okay, so that's fairly important. Now, Maxwell took 2 constants that we've seen in our study on electric fields and magnetic fields. The first is the permittivity of free space. Remember, we saw that one with our studies on electric fields. And then he looked at the permeability of free space. That's for magnetics, so for magnetic fields. And they have very similar names, but remember, you just need to know that you can look up these numbers inside your constants book. And he used these to work out the speed of light, or the speed of an electromagnetic wave. And he saw that the number they got was very close to the speed of light, and so he went, hey, light's probably an electromagnetic wave then. And they went and said, hey, yeah, you're right. Now, you don't need to know how Maxwell derived the value, you just need to know that light, like with all other electromagnetic waves, have both electric and magnetic fields. So, let's talk about our fields. We saw in our studies of circuits in video 4 of this topic that a constant electric current will create a standing or a constant magnetic field. Okay, so constant current leads to magnetic field. Because an electric circuit is an electric field, because that's what allows the movement of charge, for something to be moved, to go from not moving to moving, means there has to be a force on it, which means that if it's an electric charge, there must be an electric field, because electric fields cause forces. We saw that way back in video 2 of this topic, I think. That means that the electric field is causing a magnetic field. Okay? And the fact that was actually one of Maxwell's equations. The direction of the field will affect the direction of the magnetic field. We saw that with our learning about the right-hand rule. And a change in electric field will then cause a change in magnetic field, because if the magnetic field depends on the electric field, if we change that electric field, then we're going to change the strength of the magnetic field. Remember, the fields are perpendicular to each other. So we've got here, there's our first principle. Now, in video 7 and 8, we saw recently that changing a magnetic field will create a changing electric current. And so, therefore, a changing electric field, because currents and fields go hand in hand. Again, these are perpendicular to each other. We saw that with our right-hand rules. And the strength of the magnetic field affects the strength of the electric field, because the more magnetic strength change in magnetic field we have, the more of an electromotive force that will be induced, and then therefore there's a greater electric field. As such, from these two principles, we can see that they form a self-perpetuating system. Okay, so if we change our magnetic field, we get a changing electric field. Okay, there's our second principle. But a changing electric field causes a changing magnetic field. There's our first principle. But a changing magnetic field causes a changing electric field. And you can see this going on and on and on. Okay, it goes on for infinity. So there's a set of observations about electromagnetic waves I've copied out of the textbook here, and it's worth overlooking these and understanding. So here's our first two principles. And oscillating just means moving something, going, yeah, that's oscillating. Okay, my hand is oscillating there. An oscillating electric field generates an oscillating magnetic field, and vice versa. The planes are 90 degrees to each other. We've seen that with our right-hand rule, and we just talked about it a second ago. Okay? But here's the sort of extrapolation bit. Because E and B are both perpendicular to each other, okay, the direction of travel will be perpendicular to both, which means that an electromagnetic wave is a transverse wave. Okay, the movement of the energy, the oscillation of the wave goes perpendicular to the direction of the wave. We talked about that back in Unit 3, Topic 3. Now, next couple of bits are kind of important. Oscillations are in phase and of equal amplitude. So if I'm going to do it left to right rather than up and down, or one up and down, one left to right. So if this is my electric field and this is my magnetic field, these are not the directions, but just the strength. They will both increase and both decrease. Increase, decrease together. Think of it like breathing. That means they're in phase. They're also of equal amplitude. They've got equal size. Okay. The energy of the wave is part of these electromagnetic fields, the E field and the magnetic field. The energy in the E field is equal to the energy in the M field, which is why they have equal amplitude. Waves always go at the speed of light, and they leave the source. They can go through a vacuum, they don't need a medium. And if you turn off the source, it doesn't mean that the waves stop. Okay, so they keep going on. They're independent of the source. The source emits them, but they just keep going on. Okay. So, let's talk about the wave equation then for a second. The wave equation, we saw this back in Unit 3, Topic 3, because light, we just established, is a transverse wave. But we just also said that light travels at a particular speed, the speed of light. So we can rearrange this equation or substitute in this equation, and you'll often see this for when you're dealing with light, in that the speed of light c is going to replace our velocity for light. Remember, it is provided as a constant, but it's a very commonly used number. So if you can remember that the speed of light is 3 times 10 to the 8, it'll just save you looking it up in the back of your constants book. And they are things that, it is a number that I'd expect you to use on the final exam a couple of times minimum. There are some common values. Now, you don't need to memorize these. This is not inside the syllabus, but it's worthwhile, in my opinion, having a sort of rough guesstimate of where numbers are, so that it allows you to check. Blue is around 470 nanometers. Remember, nano is 10 to the negative 9, or if we were to see this without any sort of nanometers in front of it, it would be 4.7 times 10 to the negative 7. Green's about 550 and red is about 700. Again, you don't need to remember exactly these numbers. I tend to go 450, 550, 650 in my head, just so that it's going up in a steady increment. They're not perfectly accurate, but it gets me a quick ballpark so that I know if something is right or not when I'm doing calculations. So, pretty short one today. In the video, we've learnt that light is an electromagnetic wave made by changing B and E fields. And we've gone back to the wave equation. We've looked at some common colour wavelengths to be used on our when we're doing questions for us to reflect upon. For your entrance slip to class, please complete questions 1 to 8 in chapter 8.5. oops, sorry, this says 1 to 9. I must have missed the typo there. I believe it's 1 to 8, but just do them all. It's a very, very short chapter. And copy your answers into the 4.1.9 space on eLearn. It's also worthwhile reading chapter 8.6, which we did do in class, but it's worth having a look through to help you consolidate your learning, as it does talk about electromagnetic waves being applied for a very common scenario. So it's worthwhile taking a look at that. Thanks for listening, guys. Have a great evening. Bye.